Now we're going to look at some exceptions to electron configurations and some adjustments to the standard order we've seen so far. And to do that, let's review that the periodic table is in fact organized as an Aufbau diagram. That this stepwise feature of the periodic table with the different blocks of elements is to mimic the order of filling, or the Aufbau principle. I mean, filling from lowest energy to highest energy. And so let's return to that Aufbau principle and remember again the structure of that and how that represents what's on the periodic table. Again, we fill from lowest to highest. The 1s has to fill before the 2s, before the 2p, and so on all the way up the table. The 4s fills before the 3d, which again is why that D block doesn't start until the fourth period on the periodic table, because the 3D fills after the 4s. All right, so let's take a look at here. Once you grab your periodic table, think about what element is represented here and see if you can write a complete electron configuration for that element. Go ahead and pause the video and do that. Well, hopefully you counted that up and figured out that that was chromium. Chromium has 24 electrons, so there are 24 electrons represented there. So if we were to write that out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, and we have, of course, all of our rules filled there. Hund's rule here being demonstrated by one electron in each orbital with like spin. Now, here's the thing. Chromium is just short of having a half-filled 3D sublevel. Systems in the universe tend to proceed to low energy as a natural feature of that universe. And it happens to be the case with electron configurations that completely filled and half-filled sublevels are lower energy than any other arrangement. In part, this is due to the fact that symmetry is frequently paired with low energy. And so this 3D sublevel with the 4 electrons and then the 1 empty orbital lacks a certain amount of low energy symmetry. So what chromium will do is, rather than drop that electron in the 4s, it will steal that electron from the 4s and put it in the 3D. Now again, there is not an electron in the 4s that then gets moved to the 3D. A chromium atom is going to arrange its electrons like this, in violation of what would normally be the Aufbau principle, right? Lowest to highest energy. Because it's actually lower energy to have the 4s and the 3D partially filled, both of them partially filled, rather than the 4s filled and that asymmetric 3D with the one empty orbital. And so, rather than demonstrating this electron configuration, chromium is going to demonstrate this electron configuration ending in a 4s1, 3d5. And again, if we were going to do that with our noble gas electron configurations, we would put argon in brackets, 4s1 and 3d5. And this is an exception to our standard electron configurations for chromium because that 4s is not completely filled before we're moving electrons in the 3D, but this arrangement is a lower energy arrangement. Why? Because if it wasn't, the electrons would do something else. Electrons are always going to arrange themselves at ground state in the lowest possible energy arrangement that they can. It turns out on the periodic table, because molybdenum is in a similar situation as chromium with 4 electrons in the 4s, that molybdenum is going to steal that electron from the 5s actually and promote it to the 4d to get that half-filled sublevel. Okay, so let's take a look at another one. So take a look at this diagram here, see if you can identify this element, and write me a noble gas shorthand for this element. Go ahead and pause the video and do that. And so hopefully you sorted out that that was copper. It's going to be argon 4s2 3d9, 4s2 3d9. And again, we have this same situation, a lack of symmetry in the 3D. You have paired electrons in 4 of the 5 orbitals in the 3D. And so copper is going to do a similar thing that chromium did. It's going to steal an electron from the 4s. It's going to promote it to the 3D. Again, There is no filling in order and then stealing. The electrons are just going to arrange themselves in the lowest possible energy they can at ground state, which looks like this. And so rather than seeing that electron configuration, we're going to look at this electron configuration. Let's think about one of the ions that copper forms. Copper will readily form a 1+ ion, meaning it loses one electron. Let's think about where it might lose that electron from. And so in order to maintain that full 3D, copper is going to, rather than lose an electron out of the 3D, it will lose the other electron out of the 4s. And an electron configuration for a copper 1+ ion is going to look like this. Again, even though it's a violation of the Aufbau principle, what you have is a lower energy arrangement in the 3D being filled. This sometimes is referred to as a pseudo-noble gas electron configuration. So rather than it being a 3s and a 3p being completely filled for a noble gas, we have the 3s, 3p, 3d completely filled. So the highest energy sublevel here is the highest energy level, the third energy level, has all of its sublevels filled. And again, just like we would expect, elements in the same group are going to behave in the same way. And so you're going to get electron configurations where the 3Ds are filled for silver and gold, and they're going to look just like copper. Tungsten, for some reason, doesn't seem to do this. And it likely has something to do with the F sublevel in that 6th energy level that is filled, which doesn't seem to have the same impact on gold. Gold does fill that, what would be the 5D here. So again, it's not always completely predictable why they're going to do the things they do, but we do know that the arrangements they form are the lowest possible energy arrangements that they can have. And actually, for completely different reasons that we're not going to entirely tackle, ruthenium, rhenium, palladium also have exceptions to electron configurations. In this class, when we draw these electron configurations, we're going to draw them using the standard set of rules. We're not going to worry about their exceptions. They're a little bit harder to explain, but they do exist. Niobium also has some exceptions to its electron configuration. Platinum, there are some elements in the F sublevels for similar reasons to get half-filled and completely filled sublevels. Again, we won't go into those exceptions. The only ones I expect you to know are the chromium, molybdenum, and then the copper, silver, and gold series. The rest of them we're going to write as standard electron configurations, knowing that there are some exceptions, but I'm not going to expect you to know the exceptions, and actually I want you to show me more that you can follow the rules rather than worrying about the exceptions. That said, and the question always comes, what about P sublevels? P sublevels do not tend to form exceptions, and so the energy gain for stealing an electron out of an S sublevel and putting it into a P sublevel to get a half or completely filled doesn't seem to generate the same payoff, and so you don't tend to see exceptions to electron configurations with P when P orbitals are being filled.